Okay, good evening, everyone. So we'll start the discussions for week 10 now. So this is Adyasha Sahoo from the Department of Electrical Engineering, and we'll be discussing on this NPTEL course, Smart Grid Basics to Advanced Technologies. So we'll have a brief overview of this week's content, followed by some Q&A session, and then we'll address your doubts. So you can find the slides and the video in the links given here. So, in this week, what we started with was basically we were introduced to two simulation platforms which are more realistic because we'll see why. So, basically, what we okay, so what we do that whether we are designing some control algorithms and we are designing it through the Simulink platform available in MATLAB or so these Simulink platform what it will do, it will use the computational ability of the system that it is being used on. So when we go for computation like larger test systems, for larger systems where we want to conduct the transient studies. So as we know for the transient studies, the timestamp or the period of operation is very low in the order of microsecond or millisecond basically. So such high computations are not being able to be performed with these platforms. So to perform these transient studies for large systems, we are going for this real-time simulations platform, which we are doing through the RTDS or the Opelati platforms. So these platforms we had discussed during the hardware demonstration videos also. So what are the advantages of deploying our control algorithms on these platforms are that we can have much faster computation, that too in real time. So we can know what when we deploy our control algorithm in actual environment, how it is going to behave. That we can understand using this RTDS. Let's say you have developed some control algorithm and you want to test that how it is performing in the actual practical scenario. So to get that idea, we can run our simulations using this RTDS and OpenRT to get an idea of how effective the algorithm will be when deployed in the actual scenario. So obviously these are in continuous real time. So it will depict as if we are operating in a real microgrid system. So we can also like initiate different contingencies in the system through these platforms, and then we can have this transient studies that how the system is behaving in case of such contingencies. Hardware, they also provide this hardware in loop testing. So what is this hardware in loop testing is basically these RTDs and OpenRT, they are having, you can say, input and output pins, right? So they can receive or send the signals to the hardwares, receive or send various control signals which are calculated based on the control algorithm and send it to the actual hardwares. And these can be both digital and analog type pins. So if you remember, while demonstrating this, all this PV, wind, cell balancing, what we were doing, there we were calculating some PWM signal, like for the cell balancing, if you remember, we were calculating some PWM signal, and this was done in the Opalati or some platform, or and this PWM pulses that we received, we were sending it to the actual hardware, that was the gate driver circuit. So this is in actual in hardware. So through this, we can send to the gate drive circuit and it can operate the cell balancing for actual cells, right? So this interfacing between the software and hardware is also provided in this. So basically, because what we do is we are deploying some control algorithm for the inverters or converters. Basically, we are generating this, we can say pulses, PWM pulses, to vary their duty cycles according to our operation. So these control algorithms will calculate this PWM pulses and it will send to the actual, it can also send it to the actual hardware. Uh, did my screen just miss? I'll just reshare once again. Hello, am I audible, right? Okay, I think the screen just went off. I am resharing the screen. So is the screen visible now? Hello, is the screen visible now? Okay, thank you. So we'll proceed. So we were discussing the advantages of using these platforms for simulation studies. basically this hardware in loop and continuous real-time simulations. And then moving to the content of the week, it was first we were studying the simulation of a AC microgrid. So we have already, so yes, we have already studied the, we can say, fundamentals or the theory required, and basically here we are just studying the simulations in case of a AC microgrid first. So you can see here we are having a PCC. Basically, this will be a AC bus, and to this AC bus, which is the acting as the PCC, we are connecting various resources. So we have this PV, which is producing DC power. So we are connecting it through this AC to DC inverter. Then we have a AC load, which is directly connected to the bus, a diesel generator similarly, and a battery energy storage interface with a converter. So, why do we need this diesel generator? Can anyone tell me? In this microgrid, AC microgrid environment, why are we compiled to use this diesel generator? Anyone? Why are we deploying this diesel generator in the AC microgrid? Is it having some special functions to play here? Uh, okay. So reliable, you are saying in the context of reactive power, active power, or both? True, true. But in this context, we are having it. So we want its support for reactive power, active power, both, or why specifically? Because as you said, reactive power, I think batteries interfaced with a inverter can also give the adequate Q support, right? So why? So this diesel generator in a grid connected mode. So grid connected mode, a diesel generator, what should it play? Because grid connected means P we can get from the grid, and this Q, basically in grid connected mode, we don't require this P support from the DG, but this Q support we may require, because even though the batteries are giving us the Q support, they may not be always sufficient to regulate this voltage at this bus. So for that, in a specifically for the grid connected mode, for the Q control, basically for regulating this voltage at this bus, we are requiring this DG. And then when we go for islanded mode of operation, so in those cases, so we require both P and Q support from the DGs. And also, we had studied about grid forming, grid following, and grid supporting converters, right? So if we don't have a grid forming inverter, basically this grid forming is in research state. In actual practice, what we are having is majorly grid following. So if we don't have a grid forming inverter with us, this diesel generator will act as a typical as our synchronous generator, thermal synchronous generator, and hence it will give us the V and F for the other V reference, we can say reference signals for other converters to work. So this is the function of this DG in a microgrid setup. So as I said, in the grid connected mode, the delta P mismatch, basically delta P mismatch will be, if we consider for the previous case, so if P load is there minus PPV, so if they are not exactly equal, the excess we can always take from the grid. And in the grid connected mode, we always desire that the PV operate at its MPPT mode so that we can derive maximum power at all times. And depending upon this PV, if this, I would request to mute yourself. Okay. So basically, I was saying that for this MPPT mode, basically, if the PPV generation that we are getting is greater than the demand P load, then at those we can charge the battery to store the excess generation, charge the batteries, and in the reverse case, when the PPV is less than PL, then we may discharge the battery to supply the remaining power. Similarly, the diesel generator, it will help for the voltage regulation purposes by controlling the Q basically. Then in the islanded mode, so the PV may or may not operate at MPPT always. So it will depend upon the SOC of the battery that we have. Depending upon this SOC, we'll see it further. The PV may or may not operate in MPPT mode. And here the diesel generator will be in isochronous mode basically, and it will provide the V and F reference to the inverter connected resources in the isolated microgrid. So basically this is the control algorithm that you are getting. So this reference, P reference and Q reference in the isolated mode, we can say that will come from your diesel generators. And according to that, you will have this ID and VD control, and you will minimize the error with the help of this PI controller. Then we'll have this Q ABC. Basically, here this was in DQ frame. So DQ to ABC frame we will convert and we'll send the PWM pulses to the actual inverter. So you can say that up to this part, it will be in the software. So these actual quantities you can get through sensors basically. And this algorithm, it will be run in the software that is we had studied under the RTDS or Upalati platform. And then these pulses will can be sent to this hardware to actual inverter. So that is how we work in a lab setup basically. So there was different case studies for this AC microgrid. First one was the grid connected mode, right? So here in the case one for grid connected mode, we are considering that there is no distributed energy resources present. So basically this PV, you can see it is at 0. It is not generating anything. And we do also do not have this battery with us. Neither is this, you can say, P generated by this diesel generator is also not with us. Basically, this load of 0.5 megawatt is being directly fed from the grid because your P grid is zero point 0.5, right? So basically, your grid is feeding everything. You don't have any power from the battery, PV, or the diesel generators in this first case. Then in the second case, when we switched an additional load, so that you can see this P load has increased from 0.5 to 1. Here you can see. And in this also, we are not having any DR with us. So basically, still these are at 0, 0, and 0. So the P grid has again increased to 1 to cater to the additional load demand. Then in the third case, what we are doing, we are connecting the battery now. We are connecting the DER now. So we consider that the MPPT or the maximum power corresponding to the MPPT point is 0.4 for the PV. So as we had discussed in the grid connected mode, the PV will always be in MPPT. So here PPV is 0.4 and you can see the load is 0.5, right? So PV is 0.4, P load is 0.5, and in during this period what we are having, we are charging the battery. So this P battery, you can see it is negative of 0.3, means it is consuming. So basically here the power flow is like this. Here PV is injecting, load will draw the power here, and we'll calculate whether this diesel generator has to inject or grid has to inject basically. So P battery is minus 0.3. So from here what we can see is, if you do the power balance calculation for this, so in grid connected mode we are not switching on this diesel generators. We are not using it for active power mismatch purpose in grid connected mode. Only we take the Q support. You can see here Q is 0.5 for this diesel generator, but no active power support. The active power support will be taken from the grid. So here basically 0 for active power. So if you calculate whether this AC microgrid is in deficit or surplus, so basically your summation, if you consider the load, then that will be the actual load of 0.5 plus the battery charging, right? So that is 0.3, means your total requirement is of 0.8, and your summation of the generation, basically you have one source only, that is PV, so that is at 0.4. So roughly from the grid it has to supply the remaining 0.4. So here you can see 0.42 is being injected by the grid. So one thing it was worth noting that although the P support we are not taking in case of grid connected mode, but we are taking the Q support to maintain this voltage at this AC bus basically. Then in the case 4, where we had the grid connected mode, we had the DER, this case is PV, but it is not now at MPPT. So it is not at MPPT because it is at point 2, you can see. So during these conditions, we utilize the battery, right? When therefore we don't have enough renewables to us. So the battery is discharging. Similarly, P support as discussed, we will not take any P support from the generator and the load is constant at zero point 0.5. So load will draw, battery is now discharging means it is injecting, PV is also injecting and we don't have this. So similarly, if you see now your summation generation will be, so your PV is also injecting and your PV is injecting. PV is at point 2, so 0.5 of generation, which is exactly equal to the P load. So this P grid is near about 0. But here also you can see, although the P support is 0, the Q is non-zero. Then coming to the isolated mode of operation. So here we don't have the grid with us. So P grid will be always 0. So in this condition, we will now activate this diesel generator in isochronous mode. Basically, we will derive the P support from the diesel generator if required. Okay. So here we will derive the P support from the diesel generator in case of the islanded mode of operation. So you can see P load is again at 0.5. There is no injection from the grid that we can take, and PV is now at MPPT. Right, PV is zero point 0.4. So during peak renewable, we will charge the battery, right? Basically, we will charge the battery to store this excess energy that has been available. So again, how much? This is negative, means this battery is being charged of 0.3 and this load is 0.5. So basically, the total generation should be 0.8. And since MPPT mode of PV is given 0.4, that means the remaining has to come from this diesel generator. So the diesel generator is generating 0.4 here. So here PV is injecting and diesel generator is also injecting. Then for the second case coming, so here what is happening? This is no longer at MPPT. That means this battery has to discharge. So here it is injecting some power, but not the MPPT power. Then the battery has to inject here now, and we'll calculate whether we require the diesel generator or not. Load is at 0.5. So you see the summation of this PPV plus P battery is exactly PPV plus P battery, that is matching exactly to the P load, that is 0.5. So we don't require the support from diesel generator, but still you are getting some 0.03 mismatch. So can you guess why we are not getting exact zero? Sorry, sir. Actually, it was not audible clearly. Can you repeat? Some losses. So this is accounting for the losses in the system. And here you note from the grid, we are neither getting P nor getting Q. Then in the third case, what we are having, we are increasing the load to 1 from zero point 0.5 to 1. So here we don't have anything. P and Q both are 0. Then PV, it is at zero point 0.2. Battery is discharging 0.3. It was as in the previous case. So this additional zero point 0.5, who's going to provide? Obviously the diesel generator. Yes, sir, correct. So you can see here from the earlier case, rest are same, but now the P generation we are getting from the additional zero point 0.5 increase in load was met by this DG. Then in the second module or the second lecture, we were studying about the Q balance also we can see here, sir. So if you see now, the Q load is not present now. Q battery is not there. QPV is not there, but still it is, you can see minus 0.4 means it is absorbing some Q, right? So although I would like to, it was a nice point. So as we know, we are writing the power balance as P generation. We can say that it equal to P demand plus P loss. So is this equation correct? Power balance equation for active power? This relation, it will satisfy always, right? Similarly, if we write for Q, summation of the Q generated is equal to the Q demand plus the Q loss. So this, so is it always this will satisfy? Anyone? It should be, right? Like, what is the difference in active power and reactive power? Like, we want to balance. So, what does your instinct say about this Q relation? Will it hold always true? Anyone? Why? If it is not, then why? Like, is anything missing here? Q will be also lost in the lines, right? Like you have line parameters R and X. So this will for the P loss, and this component will result in the Q loss. So this equation is should hold true, right? But actually, uh, in the case of active power, who is generating and which is the demand is very clear, right? Like these sources will generators will generate, load will consume the power, and in the we can say delivery process, some energy will be lost. But that we can't say always about Q. Because for Q, except for your generator and load and lines, we have many other sources of Q in our system. So, do you remember about half line charging? So, basically, if you remember the model of transmission line that we consider, the pi model. So, basically, this is your R plus JX, right? And these shunt capacitors, these can basically, these are additional Q sources in the system, right? And this will depend upon the line parameter. So in addition to this Q generation by the generators, Q demand by the loads, the additional source are this line charging. So you can't say this relation will be always true. It will always depend that what amount of Q is being injected or being absorbed by these capacitors. Right, and this is not in our control. So this is one such thing that half line charging will be there. And then sometimes we have also additional reactors and capacitors installed in our power system. So those are also depending upon their status, it will be there. Then the status of these transformers, if you remember this on-load tap changing transformers, so their status is also affect this Q. So for these reasons, this Q balance is not as straightforward as P, we can say. So it will always depend upon the loading condition. It will depend upon the line parameters. It will depend upon the system components. System components, right? Like the OLTC and the shunt reactors and capacitors that we have. It will also depend upon the system parameters, this half-line charging that we talked about, BC. So due to all these, writing a straightforward Q balance equation is always, we can say, not as simple as the P, because the P sources are limited in the system, but for Q, it is very dynamic. So here you can see that although this P load is near about zero, battery is also zero, PV is zero, but still then this DG is absorbing some power. So it may be doing this for regulating the voltage, right? So it is absorb, you can say absorbing this means, can you comment upon the system condition, like in terms of voltage? If we don't inject, absorb this much of amount of power, what will happen at this V bus? So here, if you remember, we inject Q when their voltage is falling below certain threshold, right? And we require to absorb the excess amount of Q whenever the voltage is above a threshold. So here you can see it is negative zero point 0.4, right? Means the diesel generator has to absorb this. So we may comment that if the diesel generator would not have absorbed this much amount of Q, the voltage in the system would have been greater than the threshold that is allowed. Or for this MPPT operation, what voltage we require. So for that also maybe we require to absorb zero point 0.4 amount. So I hope this is clear now. Okay, then we'll proceed. So next we had this DC microgrid system, right? So in the DC microgrid, you can see here this bus is now a DC bus. So we have PV panels connected through this boost converter, DC-DC converter, diesel generators through this inverters, batteries, basically supercapacitors, and we are having wind and we have three loads. So for this case study, we are considering that one of this load is critical, which must be on at all times, and other two are non-critical type. So maybe this critical can be a hospital, it can be a military. So we'll see it in the results that how we are ensuring that this critical load is always on. Then we have two generating sources here, three basically, diesel generator, PV, and wind. But then here, can anyone guess why with battery? In the previous case, we had a battery, but now in the we have a battery plus we have a supercapacitor. So what is the need here to have both of this? Can't we have just the battery or just the supercapacitor? So this battery, slow we can say, plus we can say they have they can store for longer periods. So these batteries are used for basically storing the power or energy, and this supercapacitor they can inject and or absorb very quickly, so they will be helpful in the transient conditions. Is anyone, please mute yourself. Or is anyone asking some doubt? Okay, okay, we'll proceed. Okay, so here I was talking that in case of transient conditions, when the grid wants quick support, so in that case you will use the supercapacitors. And when we want to store the energy from the renewable resources for longer period, for we can say power balancing purposes, so in those cases we will be using this batteries. Okay, so this was the control algorithm for this DC microgrid basically. So let's say we are starting here and then we are checking if the generation is greater than the load. So if it is yes, means you have excess generation, right? So if I have excess generation, what is my instinct? I would like to store this generation in my energy storage devices, right? But the limitation is for the SOC of the battery. So if the SOC of the battery is already full, it is already 90%, it cannot charge further, right? It cannot store any more amount of energy. So here they're checking the SOC of the battery. So if it is greater than 90%, means the battery will be idle. It cannot charge beyond it, right? But if we have capacity with us, means the SOC is less than 90 degree, so the battery will charge or it will store this excess generation, and the PV and wind, they can inject the power in MPPT mode. But here we can say there will be wastage of power, because for the active power balance we will have to curtail, that is we have to operate below MPPT. That means no effective utilization of the renewables. So this was in the case of over generation. But if the generation is less than load, if the generation is less than the load, so in this case what we want the batteries to discharge, right? Discharge to meet the loads, to make this PG equal to, so this PG plus P battery will be PL. So if PG is greater than PL, then we can, what we can do? This will charge, right? Battery will charge. But if PG is less than PL, the battery has to discharge in this condition, right? So the battery has to discharge, but it will again depend upon its SOC. So if it does not have enough capacity, so if the SOC is, we are checking here, if it is below 40% or not, right? So if the SOC is below 40%, then that means the power balance cannot be achieved through the battery. We have to activate the DG. So SOC is below 40%, means battery is not enough. So we go for the next resource that we have, which is our diesel generator. But if the SOC is greater than 40%, means the battery can just discharge here, right? And the PV and the wind, they can operate in the MPPT mode. So, and then coming here, if we do not have sufficient energy in the battery, then we have to activate our diesel generator. So if the diesel generator is not available, then we have to go to A, that we'll see afterwards. If the diesel generator is available, so this mismatch between load and generation, basically, we are checking if this PL minus PG is positive or negative. So if this PL minus PG is greater than 0, right? So it is checking if this can supply this amount of power, then the battery will go into again charging mode. So before that, we will check here for this A point basically. If we don't have the battery, if we don't have the DG, then what we will do? Okay, then here we are reaching to A. That means we have to supply the loads, whatever we have, using this 40% of SOC. So it is clear that we can't supply all the three loads, right? We have to go for curtailing some of the loads which can be handled by this 40% SOC. So we'll check if the SOC is again here, if it is less than 40 or not. So basically, we're checking between two thresholds, between 40 and between 30. So if the SOC is greater than 40, basically we are going to know, then the battery can cater to the critical as well as the both the non-critical loads. But if it is less than 40, then we are checking whether the SOC is less than 30 or not. So if it is not less than 30, we can now provide the critical load, but one non-critical load only. But if the SOC is also less than 30%, we can provide power only to the critical load. Similarly, here we are again checking that if the DG is sufficient or not, right? So if the DG is sufficient, then okay, we can charge the battery. But if the DG is not sufficient, then what to do? DG is sufficient? No. That means DG plus the battery will now supply the loads. So again, with this, as we did for this part, we'll same consider here also. The only difference here is from this A point we are calculating. That means here the load is supplied only by the battery, and here it is being partly by the battery and partly by the DG. So I hope this part was clear, or if anyone has any doubt. Okay, then I think we'll move. So this was the simulation study that was done. Basically, you can see two cases here, right? So this one is for the, you can say for PV. And where is the load? The load is at E, means here, this is load. Okay, this is PL. So first we check that the load is at 3000 and the PV is greater than 3000, right? If you check here, load is at 3000, but we can say PV is around 3500. So during this time, we can say that we will have excess generation with us. So we don't require the PDG. So the PDG is 0 for here. And where is the battery? The battery is here. And the battery can charge during this condition to meet the power balance here. Then what is happening that you can see in the period of, let's say, when you're coming to this region, right? You can say from T4. So here the power is below 2000 from the PV and the load is exactly 2000. Means we don't have excess generation with us, we have deficient generation. So who will provide this deficiency in generation? So for that we are activating the DG here. And we can see the battery is also discharged in this here. You can see here battery discharged when there was not enough generation and it was charging somewhat whenever the renewable was at MPPT. Similarly, this is also one such case study you can see here. So here the P generation is about 1000 and the P load is 3000. That means the battery has to discharge. So you can see gradually the SOC levels is decreasing. And in all cases, we can say that the voltage at the DC bus has been regulated at a constant. Then moving was We had the next topic. No, in this we had interconnection of two DC grids. So why we were doing this? For increased reliability, we can say. So how the reliability will it be increased? Because whenever one area is in deficit of power, so without what we were doing earlier, if PG is low and we do not have battery, sufficient battery storage, DG with us, then we were going for curtailment, right? Curtailment of load. So that can be avoided if the power is coming from the neighboring microgrid. So basically, we have two microgrid here, and they are enabled by this bidirectional converter for bidirectional power flow. So depending upon the situation, the power may flow from microgrid 2 to 1 or 1 to 2, depending upon this generation and this load levels at both the microgrid. So such an arrangement will increase the reliability of the operation. Then for this, we had coordinated voltage control scheme, right? So we had this coordinated voltage control scheme for this AC-DC microgrid, hybrid AC-DC microgrid basically. So here for the voltage control scheme, the objective is optimal usage of different devices and to increase the reactor power reserve. So can anyone tell why we want to increase this reactor power reserve? Why it is objective? True. But a reserve means we are not utilizing this power, right? Q reserve will basically mean that if I have some Q generation max with us, and this is the QG actual. So basically, let's say if this QG max is 50 MVAR and QG is currently 20 MVAR, so I have a reserve of 30 MVAR with us, right? So in this objective, why we want that this should be maximized? So basically, when we want to maximize this reserve, so that in case of contingencies, we have sufficient reserve to activate during contingencies. This Q reserve can be activated for the smooth operation. So for those scenarios, we are saving, we can say, this Q. And the other objective is to reduce. Yes, sir. From voltage, since we are considering the Q, so here we are considering QV control, right? Voltage control scheme. So let's say there is a failure of a line or a large increase in load or some generator outage. So in those cases, voltage will be a local phenomena. Voltage is local. So what we do is, let's say area 1, area 2, area 3. So even though the active power is transferred, actively in very, it is done that within this inter area, basically, active power flow is recommended, but reactive power flow is not recommended because it leads to additional losses. Reactive power flow is not recommended. It is recommended that Q be supplied locally wherever it is demand. So Q, we require that it is supplied locally because this voltage is a local phenomena. So even if it may happen that I am injecting, let's say, 50 MVR of Q here to improve this voltage at this area, it is not at all recommended such an operation. Because firstly, injecting the Q at this location may not lead to the voltage effect at a longer distance, right? And secondly, the Q flow over such longer distance, it will lead to additional losses. So what is recommended that we maintain the Q reserve in this area so that whenever required, this Q can be supplied locally in this sub areas basically. So this is also in different standards also in India. It is mandated that it is never recommended that you are transferring the Q between areas over long distances. It is always, huh, hmm, that is why it, see, firstly, as you said, this line rating, if you consider it is in terms of S, right? That it is a thermal limit for the line. So we want always the useful power, that is P, to flow in this transmission lines. Because even if you are sending Q through this transmission line, no actual amount of power delivery is being done. But by increasing the Q in this transmission line, if you increase, what you are doing is you are decreasing the amount of P that can be transferred using this line. So, in practically, obviously, this is not being done, but some theoretical papers, if they suggest these kind of work, so it is never encouraged that for Q to flow between areas which are geographically far away from each other. So, were you trying to say this or something else? Yes, sir. So, VAR management is a local phenomena plus till now it is being done by passive elements. If you only this reactors and capacitors, they are being utilized. But as soon as we'll be having renewable integrated system, so we will need dynamic VAR reserves. So basically, what is this? We talked about Q reserve. So Q reserve can be static, it can be dynamic. So the static sources means they can supply a fixed amount depending upon their rating, right? So this static are this shunt capacitors and reactors installed in the system. But in real time, what we require is this dynamic reactive power reserves to act basically. Because it will happen that, let's say, you want a support of 45.5 var and you have a static compensator. So basically, they can provide the var in steps, right? So 10, 20 like this, 30, 40. So exactly getting 45.5 amount of var from this static arrangement is not possible, first thing. Secondly, these are also costly elements to install in the grids, and their manual switching on off will also deteriorate their operation over time. Third is that they also cannot provide beyond their rating. Let's say if you have work capacity, static capacity of 30 var, what to do if the var required is above that? They can't do anything, right? But for this dynamic var reserves, what we have is, firstly, we can provide exact this 45.5 amount of var required. Secondly, they can be done within very less operating time, and we can also depending upon the system condition, basically depending upon the P or Q support, let's say a dynamic reserve, its maximum capacity was 40 in terms of var. But now suddenly, say, let's say you want 50 var in the system. So these dynamic reserves, they can you can say there is a trade-off between P and Q. So they can, what they can do, if the system requires more Q, they can decrease their P to increase their Q to provide to the system requirement. So for these things, we will require dynamic reserves, and this can be provided by your battery connected renewable energy resources. Through the wind also, it has capability of dynamic reactive power reserve. These generators also we have. So what we do is, over long period of time, we manage the voltage through static devices, but in shorter period of time, in transient conditions, we activate this dynamic var reserves. So over long period of time, while doing the var management, we try to maximize the Q reserve, but among that also we try to maximize the dynamic var reserve, because in the case of contingencies, these will be more helpful over the static ones. Okay. Okay, I think, yeah, so this dynamic var management, it is possible through this inverter based renewables, like your wind farms, then inverter connected PV battery systems. Similarly, your Q support from your synchronous generators are also type of dynamic var. No, sir, it will be static. Basically, synchronous condenser is not having P, right? We are, it is a P0, and Q synchronous. It can be called actually midway, because firstly, it can provide the smooth control, right? Basically, it is not in steps. It can provide this 45 MVR, but beyond a certain rating, it cannot weigh in. But we can, sorry, I want to correct. Synchronous condenser, you can call it as also dynamic, because it will allow the smooth control over, right? Like you want any in between quantity also it can provide, whereas static they can only provide certain volt levels of support, not the between quantities. So I hope you got my point. Okay. So this types of CVC, it can be centralized, it can be decentralized. So we know that centralized, we have discussed, it fails. Single point of communication failure, it is a disadvantage. But here we know the global variables, and in decentralized, there we don't have the knowledge of global variables. We have only the local variables to work with. So basically, these are the devices that we are using for VAR management. Uh, Firstly is this OLTC. So basically, if you consider a microgrid like this, so the OLTC is at the substation. So since it is a radial system, whatever the voltage at this substation, it will detect, we can say it will detect what will be the power, what will the voltage throughout this microgrid. So let's say if my voltage here at 1.0 and at this far end is 0.98, 97 basically. So if I increase the substation voltage at 1.1, it will be reflected in the uh, farthest end by not linearly. I am representing here linearly, but basically the idea is as you vary the substation voltage here, the same can be reflected throughout this radial structure. So this OLTC is basically installed at the substation, and it will be varied whenever, let's say, the voltage here decreases beyond zero point 0.9, and let's say at that time means to increase this voltage above zero point 0.9, we have to increase the substation at the voltage at the substation. So that can be done by OLTC. So this is here OLTC. And we see that each basically this OLTC has 16 tap positions, and each tap position can reflect a per unit voltage change of 0.00625. Then we have this DFIG for Q support, we have STATCOM, DSTATCOM, and we also have a DC microgrid with us since we are talking about AC DC microgrid here. So here we can see the test system that was taken. So this is a 33 bus distribution system standard. And here in the 22nd bus, we can see we are connected a DSTATCOM, and also we have this DFIG at bus number 22. We are having switchable AC loads at bus number 22. Then we have OLTC at bus 1. Then what we have at bus 5, we have this DC microgrid. So I hope the system is clear. So we have DFIG, DSTATCOM, OLTC, some flexible loads, and a DC microgrid connected to this AC distribution system of 33 bus. So the operating states of the grid, it is divided or categorized into three states basically. So in state 1, that is the steady state, where the Q requirement is less than 40% of the rating. Let's say you have the previous slide, we saw that Q rating is 0.8 MVA. So the Q required is less than 40% of this. Then we say that we are in steady state condition. But as soon, and here the voltage is maintained between zero point 0.9 to 1.1. But as soon as a sudden contingency is taking place, we can say, and there the voltage is falling, we can say, that means we have to increase the Q requirement. Means here we can say that the Q will be 30%, 35%, or 20%, something less than 40. But here we mandate that the Q should be 40% of the rated. Right. And in the third, this is the in case of transient case. So whenever there is extreme deviations in voltage, that is, you can see here, the voltage falls below zero point 0.9. That means the system is in high alert state or there is high requirement of queue support. So in these cases, we allow up to 100% utilization of the devices for regulating the voltage above zero point 0.9. So basically these are three states. State 1 is your normal steady state where Q is less than 40 and V is maintained. 2, also there in this state, let's say some loads have been switched on. So that's why voltage is also maintained here, but the Q requirement has increased to 40%. And in 3, so this will happen in case of certain contingencies when the voltage will be extremely low or voltage is extremely high, so that we want full Q support of 100% from all the resources to retrieve the system from this condition. So the comparison has been done between what is the existing, and first we'll see what is existing way of this coordinated voltage control basically. So here we start from here and we are measuring the voltage, right, from this OLTC and STATCOM here. And if we see that the voltage is maintained between this limit, that means we are in, we can say, state 1 or state 2, which was the steady state or dynamic state. Right. So once we know that the voltage is maintained, so either it is in steady state or it is in dynamic state. So then we'll check that if the voltage is exactly at 1 per unit. So this is the ideal case, right? We want this flat voltage always. So if the system is already at this condition, we don't want to absorb or inject any Q. So we set the Q as 0 for all the devices. But if the voltage is not at 1, then depending upon the system, so if it is in steady state basically, that means the Q required is less than 40%. So if it is yes, then the Q has been provided from these resources. Okay. Okay. So if the Q required is less than 40%, means it is in steady state. So the Q is provided by these resources, right? But if it is no, means that means Q is equal to 40%, that is in your dynamic state, right? So we, if the Q is limited at 40%. Similarly, if the voltage is not within this boundary, means we are at the transient state. So in the transient state, we are utilizing 100% capacity from all the resources. So, okay, this is what the existing. In the proposed scheme, they want what they have done is they were doing in the first stage, they are identifying the grid condition, that is the VM. Then they are deciding the role of the voltage control devices, whether they will act as a master or as a slave. So basically, for this dynamic and the steady state and dynamic state conditions, we'll be utilizing the OLTC and DC microgrid. While for so these are available during these states and during this wind and statcom. So they are available for both the three states, for the steady state, dynamic state, as well as transient state. And the third thing they are suggesting that they are allowing a delay. So why we want this delay? Can anyone tell me between two devices? True, but this delay is meaning that we don't want that OLTC StatCom to start simultaneously. Means at t equal to 0, we don't want both of them to start. The delay, what we mean is at t equal to 0, let's say OLTC will start, and these are slow devices. So maybe it will take some 5 time steps to reach to its final, and after that only they will deploy the StatCom. So that is what they mean by delay. But then why they are suggesting this? What is the problem if we go this way by activating the devices simultaneously? The fastest reserve first you are suggesting? No, but here it is being suggested that OLTC will be operated first and then StatCom. So basically, what we want when we are, let's say, over this 15-minute time window, you want the voltage to be maintained, right? So let's say over this 15 minute, you calculated something, and at this t equal to 0, we operate the OLTC. Why we start with the slowest is because it will take the most amount of time to improve the voltage. So if there is a voltage fluctuation at, let's say, t equal to 10 minutes, and you turn on the OLTC at that instant at 10 minutes only, let's say voltage is not regulated, and then you will start the OLTC, then it will take very long amount of time to settle. Like, but if you know that at t equal to 10 minutes, we may require the voltage support, right? So at the first hand, we apply the OLTC so that when you reach the actual delivery time, at that time the OLTC would have the time to act so that its operation is completed. So we start with the slowest basically, and then we move to the fast ones, because the fast ones we always want to preserve them for transient periods, because let's say in between also a fault took place here. But if we all are consuming all our dynamic resources at t equal to 0, then we can't do anything at this fault, right? Because you have depleted your dynamic resources, and the slow acting devices, they cannot improve the voltage suddenly. So for that reason, we are starting with the slowest one, and gradually we will save the dynamic resources of the fast acting ones till they are required in the transient periods. And okay, that is one thing. And the second thing is why we are not going that we are simultaneously activating the STATCOM and OLTC at t equal to 0. If we know that at t equal to 10 that voltage is required, if we start both of them simultaneously, what will happen is it may happen that there will be, we say, a hunting effect. Basically, this may lead to overactivation of the devices. because you did not wait for the OLTC to reach to its, we can say, final value. Maybe it can happen that only with the OLTC the voltage has been improved. But since you had also activated the STATCOM, it will lead to misuse of those devices, we can say. Or it may sometimes happen that voltage, it will improve, but it will improve beyond the threshold. So it will again lead to this contingency. So is this clear? Was this okay? Okay, so this is proposed here, that's why. Then the proposed scheme. So here what we are doing, again we are checking whether the voltage is within limit. If it is within the limit, then here in the earlier there was no delay period, right? So here we are introducing the delay period, and you can see fast first this OLTC is acting and this DC microgrid is acting. So if the delay, they are waiting, if the delay period had not passed, then they are setting the Q as 0. And if the delay has passed, and after that they are checking the voltage. If the voltage is 1, means they don't have to do anything, right? Here, if it is voltage, that means they don't require Q. But if the voltage is not 1, then they will check if this OLTC can provide the Q required. Basically, if the Q OLTC is greater than the Q required. If yes, then the, we can say it is set at that value, right? No, if it is not, then uh, we have to operate. So this was for the solid DC microgrid. So yes, if it is yes, then the Q is being supplied there. Then similarly, it is done for this wind-based DStatCom also. Similar, you can see same phenomena is going here. But here, again, we are checking for the dynamic state and steady state. So basically, if it is less than 40%, it is steady state. If it is greater than 40%, so we are limiting this Q at exactly at 40%. And if the voltage is violated, then it is basically transient state. So in the transient state, you can see the fast acting devices, they are deployed first. That is, they are acting as masters here. But if you see here in the steady state, the fast devices were slaves because voltage is maintained here. We don't want fast control here. Voltage is maintained already here. But here, voltage is not maintained, means Q is required at a urgent level. So the master devices are the faster devices. Immediately you require the Q support. So hence the STATCOM is a master here while the OLTC is a slave for the transient state. And then these are some of the simulation results. So here basically you can see uh, the basically in the first condition at t equal to 1, you can see the PV output is more and the battery is basically charging here, right? Means we are having excess of PV because you can see the load is here somewhat around 1.5, but the PV output is greater than 1.5. That's why the battery is charging here in the first time period. Similarly, at t equal to 2, you see that the voltage, the power at the DC load that they require, there is a sudden increase here. Transient is there. So that's why certain reactive power is being supplied by the DC microgrid to regulate this voltage. We can see here. So here also again certain transients in the DC load which has activated this reserve, dynamic reserve basically, leading to this voltage dip which was improved. Similarly, if you see for state 1 and state 2, means your voltage is maintained here basically for the steady state and dynamic state. So if you see that the number of OLTC switchings, then for the proposed you can see it is basically switched on once and twice, and for rest of the period it is maintained constant. But in the existing CVC method, there was frequent switching on of the OLTC. So it will deteriorate its health, we can say. Similarly, here in some transient conditions, the delay time has been introduced here. You can see here the after certain t delay only the reserve has been activated. Similarly here also. Then moving forward, we have the bus voltages. So if you see the proposed scheme, it is between 0.96 to below this one. So we can see this is 0.99. While the other methods, it is going beyond 0.94, about 0.92. So we can say the voltage is improved using the proposed scheme. Same you can see everywhere. And next thing we observe is this delta V that is being provided. So you can, this is the zoomed version of here, what is happening here. So the proposed scheme, using this proposed scheme, you are reaching to 0.98, that is near to 1, while the other methods it is below 0.98. So again it is showing that the proposed is able to give a better voltage profile. And here some transient observation have done in the state 3. So here you can see reactive power in the transient state. It is being provided by the fast resources, by the STATCOM, by the wind and the DC microgrid. And in the other cases, they are ideal because if we had studied in state 1 and state 2, we are utilizing the OLTC as the master. Then next, we had studied about this parallel operation of inverters. So in the parallel operation of the inverters, we saw that why we require this parallel operation firstly is because as the number of this VDC is representing, let's say PVs, they are getting added. Similarly, the inverters, they are also being added in parallel. So these inverters, they are being connected at this BCC, and this is the filter, we can say LCL filter, and they are delivering the current I21, I2, I2, I2N. Basically summation of this current I to I, where I is varying from 1 to number of parallel connected inverters, and that will be equal to this I grid. And this is the grid side inductor basically. So what are these challenges in this inverter operation we studied was, let's say there was one inverter and there is another inverter. So when they are being connected in parallel to provide the grid current, V grid, L grid. So basically this component, if we say I21, I22, it is having two components. So one is called the interactive component, that is only flowing between these inverters, not going to the grid side. Other is the common current component, which is flowing to the grid side. So this is the common current. So these interactive currents, so basically if you this I21, I22, let's say this is the voltage source 1, this is the voltage source 2, so that will be some gain matrix times V01, V02. So basically this I21 is G11 times V01 plus G12 times V02. So this is the interactive component, we can say, which is affecting the current of this inverter due to the voltage source 2. Similarly, in I22, you will get G21, V01. This will correspond to the interactive component. So, and these G matrices, they are calculating using this superposition theorem that we all know, that when we have multiple sources, then we can write that as a sum of activating one source at a time and observe, then adding their effects, we will get as if the devices are activated in a single time instant, right? So what we do for voltage sources, we short circuit them. For current sources, we open circuit them. So we had voltage sources here, so we can once short circuit V01 and calculate the effect of V02. Similarly, another instant we will short circuit V02 and calculate the effect of V01, and then we'll add this two to get the characteristics when both V01 and V02 are present. So here you can see here V01 is there, V02, and this I21, I22, they are forming this I grid. So when you do some rearrangement of this, then finally what you get, the interactive and common current components as these expressions basically. So in the hardware demonstration, you saw that this I reference, it was once set that I reference 1 is equal to I reference 2. Then in that condition, there will be no interactive component and only common component. And in the second case, they were set not equal, and there you could observe the oscillations in the oscilloscope, because if they are not equal means this will be non-zero, so there will be interacting component flowing between the inverters. So for the stable operation, what they are suggesting that these system, the poles should be in the right hand plane of the S plane for system stability. So if you remember the concept of control system where we convert this into S and J omega basically excesses. So the negative right half of S plane, we know that this negative real part is stable. That is left. That is stable. So if you have the poles of the system in this region, then it is a stable system. And if you have S equal to 0, then we get here oscillatory response. And if you have positive, that is poles in the right hand, then it is unstable. And here it is marginally stable, right? Marginally stable. That means here if you get the response vaguely, if I say, so there you will get damped oscillations. Here you will get sustained oscillations of equal amplitude, and here the amplitude will increase. So for without to be stable without oscillations, we want that these poles should not be in the right half of S plane. Then we had studied about harmonics in the system. So here the cause for these harmonics are basically these nonlinear loads that we have, the Polytronic load, the switches, converters, etc. They are contributing to the harmonics in the system. And due to this harmonics in the load side, they are being reinjected in the supply system. So these will lead to extra losses and heating of the system, and also it can interfere with the communication system. So these are certain types of harmonics that were discussed. This is your ideal case where you're getting perfect sinusoidal, and this is the voltage sag, means the voltage is reduced. Swell, voltage has been increased. Similarly, interruption means no power, no voltage. So these are some we can say power qualities issues for the voltage. For the current, similarly, this is the ideal case. Here, due to nonlinear loads, you are getting harmonics in the current. So in the notch means you can observe these notch. So this high frequency oscillations, these are basically notches in the system. Then these are phase unbalance. Due to phase unbalance, you are getting similarly phase jump. You can see one phase has been. Then to mitigate this, we are using filters. So similar to this static and dynamic reserves, so same kind of concept you can also apply here for the passive filters. So these are, you see, fixed type, no, fixed RLC, using fixed RLC. So these are shunt, series, and hybrid combinations. And then due to their disadvantages, what disadvantages? Firstly, obviously, they cannot adapt according to the system basically, because these are fixed quantities, we can't change them. Then their size is also high. So we are going for active filters which can actively adapt to the system conditions. So these are shunt active filters, these is series active filter, and this UPQC, Unified Power Quality Conditioner. Here you are using a combination of shunt and series type. So the shunt filters will mitigate the harmonics in the current. The series will mitigate the harmonics in the voltage. And for UPQC, we will get both. So this was the setup that was studied. Basically, we got a nonlinear load here, and here we have a series active filter which is connected through this LC filter and the series transformer, and the shunt filter here it is connected through this shunt inductor. So basically, depending upon the control algorithm that you have in the FPGA based controller, the duty cycles or the pulses will be sent to these filters to, you can say, limit the harmonics that is being injected by the nonlinear load basically. So this shunt will work, it will provide low impedance path for the harmonics to flow, so that the harmonics will flow this side, but this series one will provide the high impedance so that this harmonics is cannot flow back to the supply system. So moving to the question and answers. So first question is, which of the following is responsible for providing the reference AC voltage and frequency in an islanded AC microgrid? Okay, one diesel generator. Anyone? It will be diesel generator. It is correct. We studied that in the islanded AC microgrid simulation results also. Loads obviously they cannot provide, and this battery and this PV, it will depend upon the type of inverters, whether they are grid following, feeding, or supporting type. But these diesel generators will operate in isochronous mode to provide the voltage and frequency references for these PVs, batteries to operate. So this is the right answer. Then a diesel generator is capable of injecting P only, injecting P but at the cost of Q always, absorbing Q, injecting P and Q. Yes, true. This also we had seen in the case studies that sometimes it may like inject active and reactive power depending upon the system condition, and these are not dependent for a diesel generator. Then the wind generator output is processed through dash to feed power to a standalone DC microgrid system. To a DC microgrid system. Yes. So it will be AC to DC, and then since we are connecting to DC microgrid, we'll be having DC to DC stage here. Then in a two inverter system with similar inverters, if the current references are equal, then which of the following current will exist? Yeah, so we saw here, since it was IREF 1 minus 2, so if they are equal, then this will not exist. This will be 0, and only the common current will increase, will exist. Then again, the purpose of a diesel generator in IC microgrid is regulate voltage, regulate frequency, supply power to loads during low renewable. Yeah, so it will perform all these functions basically. Then a battery and supercapacitor are connected to DC microgrid through boost converter, buck boost converter. Okay, we got one buck boost converter in here. So basically, we want here bidirectional power flow. So that can be achieved through buck boost operation, because in boost means you can always feed the power in one direction, and since depending upon the state of the system, we want to inject or we want to absorb, so bidirectional operation can be done through buck boost converter. Then interconnection of two local DC grids is feasible for equal voltages of both grids, unequal voltage, both or none. Okay, we got one, both. Yes. So we had also seen in the lecture basically, there we had connected unequal voltage microgrids. So one was around 390 or 380, other was at 48. So it is independent upon the voltage. It may be equal, it may not be equal. No, both the cases, the interconnection is possible. Then, what is the disadvantage for passive filters? Limited capability with system, cannot supply active power, cannot mitigate current related power quality issues. Okay. Okay, we got one. Yeah, because they are of fixed rating, so they cannot adapt with the system changing conditions. So this is their disadvantage, due to which we are going for active filters. In the D STATCOM, in a unified power quality conditioner acts as shunt passive filter, shunt active, series passive, or series active. Yeah, it will be shunt. Yeah, so this is an active filter we had seen. So STATCOM is a shunt active, acts as a shunt active filter in this. So this is basically a hybrid filter. In that, STATCOM acts as the shunt component. So which of the following of inverter current is independent of grid side impedance? Interactive, common, both, or total grid side? Okay, we got one. So if you go back to this derivation, so here basically this GP and GC, so it is GP does not so grid side means this LG, right? So it does not con, con it is not having any component of this LG, whereas this common current it will have a feature of this LG. Because one thing you can see here, this LG current is only flowing through this part, right? I common. So it will be influenced by this, but this interactive is only limited to this loop. So it will be not depend on this grid side. So here we can say that independent of grid is this interactive component. Okay. So which of the following is the most critical state requiring active or reactive power support? Sorry, voltage or reactive power support. So basically in these states, we saw that the voltage was within the limits, but here the voltage limit was violated. So for that, we were dispatching all the resources at 100%, but here we are limiting to 40% since the voltage is maintained here. So if you consider that most critical state, it will be this transient state. Okay, any doubts? Okay, I think then we will close the session and we'll meet in the next week probably. Thank you for joining.